Welcome to this presentation for the Laboratory for the Certification of Asphalt Technicians. We will be talking about the Asphalt Technician Certification Program. We will go through some introductions about the CAPA and RMEC staff, the LabCAT Board of Directors, LabCAT Technical Committee, a program description, safety, and some general information. This is the CAPA and RMEC staff. This is the LabCAT Board of Directors, our LabCAT Technical Committee. The Technician Certification Program is broken down into 6 basic parts. Level A laydown is what we're going to be talking about today. Certification Level B, Plant Materials Control. Certification C, Volumetrics, Gyratory, Stability and Allotments. C- Design, Volumetrics, Gyratory, Compaction. E, Aggregates, and I, Asphalt Inspector, are all separate and individual programs that we will not be discussing today. Certification schedule for Level A is generally done on Tuesdays. However, sometimes we do a Level A only, and those days vary. They all begin at approximately 8 a.m., and we start with the classroom presentations. The classroom presentations are as shown on the screen. Take note of the CP numbers, or the technician responsibilities. The CPs are Colorado procedures, and they are all pertinent to what will be done in Level A. Those need to be looked at, and they need to be well understood before going any further into this program. We will talk briefly about each one of those in the presentation today. However, having a better knowledge of them will benefit you when you take the written test. The written test is a 60-minute timed test with a maximum of 60 minutes. Level B is generally done the second day, or during our normal certification, standard certification week, it would be Wednesday. Level C is typically done on the third day, and during our standard certification week would be the third day. And you can see all the procedures that are entailed in Level C. Requirements for what we're doing today is just relax. It's important that you relax, that you can gather as much information as possible from the presentation as it's going along. When we have breaks, please come back. You won't have a break during this. You'll be able to stop the recording and then pick up wherever you want. Comments and questions are going to be tough since we're doing this as a recording. If you do need CEUs, we can get you those. You have to send us an email to rmaec@co-asphalt.com. When we get into some of the lab proficiency things, there are safety issues, but none of them are involved in Level A. General information we will pass by. There are handouts available for this, the slide presentation, which you should download from the CAPA website under the LabCAT page, and download the presentation for Level A. The CDOT manuals are available on the CDOT website, and we suggest that you go out and pull those down so that you have all of the CPs and the field materials manual as necessary. As I said, the written test will be done at the end. When we do this in the classroom, they are manually given tests. If we're doing this as an online, they will be electronic testing. Again, 1 hour time limit. You have to have 80% correct of all questions in order to pass. So some of the procedures that we need to be looking at. We want to make sure that everybody has passed the procedures, that passed the written test prior to moving into the proficiencies. If you have not passed the written test, you will not be allowed to proceed to the proficiency testing. It's important that everybody does pass the proficiency test as well in order to become a fully certified LabCAT technician. I've skipped through some of the slides because some of those are important when we're doing this in person, but if you're just using this as a training tool, we don't need to talk about those at this time. We do use proctors, and we will be using proctors in our proficiencies for our proficiencies, whether they are in our facility or at another facility. Our proctors come from CDOT, local agencies, contractors, and consultants. The time that it will take to get everybody through the proficiencies will depend on the number of proctors and the number of stations that we have. Presentation information that we have today is based on CDOT procedures, and where it's indicated by blue type, those are very specific to CDOT and vary from the AASHTO procedures. All of our information is based off AASHTO. In any situation where the CDOT procedure is present, it will be superseded over the AASHTO procedure, and you will be tested on the CDOT procedures. We will get going with level A procedures. We're going to first talk about a process control program. And why is it that we have to make sure we have accurate sample splitting and testing on any projects that we are working on? If we don't have those accurate samples, it doesn't matter what we are doing. We can pull a sample, take it to a lab, do the best that we can do in the lab, but that doesn't necessarily correlate back to the materials that are being placed on the project. So we have two different things that we look at are the owner's acceptance, and they have a planned and systematic action. There is a very strict and rigid guideline of what they're going to do, how much material has to be sampled, when it's going to be sampled, and how it's going to be handled. Process control will work within the owner's acceptance guidelines, but they will then do much more testing, sampling, and testing to get the project to where they feel comfortable with it in between the samples that are required for owner's acceptance. The contractor must develop a PC or process control program for each element listed in Table 106-1 of the Project Special Provisions in the CDOT manual. It talks about the frequency of the test result charts, and the quality level chart. The OA program is going to provide for the acceptance program, the frequency guide schedule, the identification of the specific sampling locations, project verification, sampling and testing, independent assurance program, the project material certification, and retention of the sampling and testing records. So the tester's responsibility in the acceptance program is to conduct the sample splitting and testing according to the proper procedures. They input that data into the laboratory information management system that CDOT has, and they are required to have a current LabCAT certification in order to do so. The amount of material that they can put in is based on their level of certification. It's also important that the testers be communicating with the contractor and with the owner. So samples are very important because if you do not have an accurate sample, you do not get accurate results. Accurate results can cause undue stops in the project, or they can also cause for product that is not within the specifications to be overlooked and to be moved on from. This is just showing some charts that are called an MQL, or a moving quality line chart, where you can see all the numbers and how they vary, but the contractor is achieving his MQL. Several examples of that. We won't go into those in any more detail at this time. Why are responsibilities of a technician so important? Because, again, the test results obtained are the basis for the contractor's incentive and disincentive, and they help determine the overall quality of the material being placed. The first of the procedures will be random sampling of materials, CDOT's procedure CP75. It's also known in the ASTM, the Association for Testing Materials, of 3665. It's going to cover random selection of materials to be sampled and tested. The sampling and testing procedures need to be followed, and they are specific to the procedures of the test required. Sampling is one of the most critical steps of the materials testing. Most CDOT specifications call for using a stratified random sampling process. It ensures that any portion of the material being taken will represent the entire lot. There is bias introduced when there is judgment, when somebody goes out and just picks a spot based on look, feel, or smell. They have to be randomly chosen so that there is no bias. The importance of ratified sampling of the materials is if it is not chosen randomly, the test may not reflect the characteristics of the product as we spoke about earlier. Stratified random sampling requires that one random sample be selected from each sublot and assures that the samples are taken in a satisfactory manner and throughout the entire production process. No material is excluded from the chance of being sampled. It is the nature of random sampling that some samples will represent below average or above average material, and the random number schedule should be determined, not determined, but not predetermined, and not shared with the contractor before the sample is taken, so that the contractor or anybody sampling has no idea where it's coming from, and it is truly a random sample. It is the responsibility of the tester to ensure that they have a minimum frequency of the sampling and testing. CDOT's random schedule can be used, and it's found in Asphalt 03 or Voids 03 computer programs under Tools. However, those programs have been phased out or are being phased out, so they're getting harder to find. CP75 contains a complete set of instructions how to access those two programs. There's also a random sampling chart within CP75. Other things that can be used for random sampling are simply a clock, a watch, or a set of dice or other things that would create random numbers so you could create a random sampling schedule. As stated before, random sampling times and locations should not be shared with the contractor. It's acceptable and encouraged for the contractor to take a split sample or to perform density testing that coincides with the QA or OA testing schedules. Most contractors, when a random is being taken, will also take a split sample from that position. Sampling should take place as close as possible to the values represented on that sampling schedule, and they should fill in the taken at column on the scheduled chart so that everybody knows precisely or as close as possible where those samples are being taken. Major deviations from the sampling should be noted and explained on the notes for the day. This is just two examples of how sampling can be taken. You have just random sampling, which may bulk samples together, where you might have samples that get bulked closely together and then one further out. Or CDOT uses stratified random, so you have a full lot, the day's lot, and then you have sublots, and you have to get a sample with each of those sublots. Our next procedure is sampling of aggregates. CDOT's CP30, AASHTO T2, and ASTM D75. We're going to talk about the sampling of raw or bulk aggregates used in acceptance and quality control from the point of acceptance, designed for the construction, materials including base, coarse, and aggregates for asphalt mixtures. Sampling is equally as important as the testing of any aggregate material. If they're not taken accurately, those test results will give you results for the sample, but they may not reflect what is actually in the piles or on the ground being used. It's important that the sampling technician avoid segregation, and they have to be selected from all the material being produced versus based on CP75. Aggregates used in asphalt have to be sampled by the contractor and witnessed by an authorized state or owner's representative. Samples for preliminary approval or production may be submitted by the producer, but they have to read and consider CP52, the contractor's mix design procedure. There are several places that sampling can take place. This is showing 6 of the accepted sampling locations. From a belt discharge, which is not common, so we will not talk a lot about that, but a belt discharge is they have to shut down the plant, go in, using the proper tools, sample from the belt, and get it done. when a plant starts running, they typically will not shut it down. They will keep the plant operating. So sampling from a belt at this juncture is not common. Automatic belt samplers, again, not common. We don't see that very often. It is a procedure that you need to understand. You need to understand the procedure and how it works. Belt discharge, again, using power equipment. This can become a sampling place. They have a bypass chute on the belt. They will run material into the front end or into a bucket of a loader, place it into a small pile, flatten it out, and then sample from that pile. This is how this procedure is done, dumping it out of the bucket of the loader, then flattening it into a pile no thicker than 1 foot, sampling it from at least 3 locations within that pile so that you get a random picture of what it means, combining those 3 portions down to create 1 sample. This is an automatic belt sampling device, again, not common. It sweeps the belt up here, pushes the material into this tube, then it's collected down here, and this is an automatic gradation house. Again, not a common sampling procedure. This is a bypass chute, again, not common. They slide this bucket in, picks up the sample, slide it back out, and they have the aggregate sample. Getting a sample from a belt, dumping it into a container, then it falls into a bucket. Again, not a common practice. Bin discharge is not used for acceptance testing, therefore we will not talk about it. You can use a dry batch. They run a batch through the plant without adding binder or any other additives to it. Bring it out the backside of the plant, dump it into a loader, put it into the small pile, and sample it from the small pile. Stopped conveyor belt, again, we don't see this very often. CDOT requires 1 or more samples between the 2 templates. Slide this template in, get it down to the bottom of the belt, so it's not allowing any of the materials, clearing the belt using a broom and dustpan to get all the fine particles off of the belt. The distance between the templates will yield an increment, and it may or may not be enough material, so you may have to take a second cut or a third cut to get enough material for what you need to be testing. You can see our technician here is cleaning the belt using a brush and a dustpan to get all the fine particles. Once all those particles have been collected, if you have more than 1 cut, you would combine those for one sample. From a stockpile, you'd want to avoid the outer edges of the stockpile, and it's important that you follow all safety guidelines when you're in and around a pit or a plant. Sampling should be done under the direction of experienced personnel. Mechanical equipment should be used whenever possible. By using power equipment, taking a loader, scraping in from the bottom, moving up the pile, exposing a representative face, channeling the face, going in, putting it again into that small pile as we talked about before, no greater than 1 foot thick, sampling at 3 locations, and combining all those portions. In a stockpile manually, you obtain the portions from the bottom third, top third, and midpoint of the pile, and then you go over the other side and you create another set, so 180 degrees over. So you're going to get 6 portions in that pile and combine them to create 1 sample. If you have coarse and mixed size aggregates, you would place the shelf upslope to keep any materials from sliding in. Remove the top 6 inches because it's probably segregated. Using a flat square end scoop or shovel, sample to the full depth of the shovel. If possible, again, use the power equipment, create yourself a mini pile and sample from that. It's much easier and much safer. This would be a plate in the pile. We're then going to scrape the materials off here, 6 inches, scooping in to get our sample and get one portion from each of the 6 locations combined to create 1 combined sample. Fine aggregate piles, use same as the coarse or mixed size, or you can use what's known as a sampling tube. You take a tube and you shove it into the pile. It is a 3/8, any 3/8 or minus material is the only thing you can use this for. The tube has to be 1.25 inches in diameter and at least 6 foot long, and you push it in a minimum of 5 locations. It will probably take more than 5 locations to get the amount of material you need, but a minimum of 5 locations. From the roadway, this would be for base course, using some type of a template or device. 3 approximately equal increments, using a flat, square, and scoop or shovel, digging down through the full depth of the material, making sure you don't get into the underlying materials, which would affect the gradation, combining all those portions, and returning them to the lab. From our windrow, again, should have enough moisture to hold a near vertical face. Removing the material from one side of the windrow to the full depth, channel up the exposed face, not losing materials off of your shovel, dumping them into your storage container or bucket, doing that from at least 3 equally spaced locations, using that flat, square, and shovel, and not losing particles off of the shovel. The last place would be cover coat or material spreader. This would be in the instance of chip seals or things like that. The spreader has to stop. You can put down tarps or other templates down on the road, let the spreader run over it, pull your samples up off that, taken for a minimum of 3 locations or from the gates of the spreader. If there's a belt transfer device, that is also another acceptable place to take the sample. Under the engineer's approval, it may be sampled from a stockpile. Here's a definition for aggregate. This is CDOT's item 403. Maximum particle size, and this is important. Nominal maximum particle size is 1 sieve size larger than the first sieve to retain more than 10% of the aggregate sample. This is an important definition for everything that we will be doing within this industry. So understanding and memorizing this is important. This is an example of nominal maximum particle size. The first sieve size to retain more than 10% of the size. So you look at sample A, and this would be a 3/4. B would be a 1/2 inch, and C. Sample size requirements are based on the nominal maximum particle size and can be found in Table 30-1 of the Field Materials CP manuals. The next procedure is CP41, sampling of asphalt paving mixtures. Again, the significance that it is very important that we do this accurately to represent the entire sample. Samples have to be sampled by the contractor and witnessed by an authorized representative of CDOT. So there are 3 different places or 3 different methods: tube sampler, at the point of delivery, or the roadway after compaction. Tube sampler is at the plant, commonly called a swing arm. The material is a bucket is put on the arm. Before the material is being discharged out of the silo, they would run the bucket out to the middle of the flow where the anticipated flow is. Turn on the flow, they pull it back, empty that bucket, do that as many times as needed to get the amount of material. The second method is to simply push the swing arm through the flow, which is very difficult, very hard to do, and to get an accurate sample. Swing arm pushed out under the flow. The material is allowed to flow. The swing arm is then pushed through the swing arm until it fills and then brought back. CDOT specs for sampling cans are 3 to 4 gallon can. That's for heavy, that's for the weight, so that nobody gets hurt when they're moving those cans. From the point of delivery, windrow, paving machine, spreading screws are the mat behind the paver. 3 or more random locations based on CP75. From the one side of the windrow, expose the center, take the shovel, take it from the bottom, rake it up, fill the shovel, do that as many times as necessary, and you do that from 3 locations, combining all of your samples into one sample. So we have a windrow being built, our technician exposing the center of the windrow, taking the shovel from the bottom and moving it to the top. From the auger chamber area at the paver, the augers have to be operating 80% of the time. The auger area should be at least 2/3 full. shovel going in, material being flowing on to the shovel. Get as many shovelfuls as necessary to fill your bucket. At least 3 shovelfuls, but it's generally going to take many more than that, especially if you're going to fill 2 buckets to split between 2 labs. Behind the paver, a scoop with sides, some type of a sampling container, shovel, and a container to hold the material. Random method, at least 3 approximately equal sized samples are increments. The increments have to be the full depth, and templates can be placed. So in this case, we've got our technician out here creating the sample, doing it with a blunt end shovel, 3 equal increments across the mat to get a sample. After compaction is typically done with some type of a mechanical device, a saw cutting or coring, and those have to be again done in a random method, and you need at least 3 samples to create an overall sample. Our next procedure is CP44 for the bulk specific gravity and percent compaction of a compacted bituminous mixture. We're going to look at how to determine a bulk specific gravity and to calculate the percent relative compaction of a hot mix asphalt mixture. We're also going to be using these for air voids analysis. The bulk SPG, or bulk specific gravity, is also used in determining a correlation factor for nuclear density gauges when they're used for testing of the in-place density of the asphalt. We have method B, the rapid test method, and method C, the core dry method. The specimens need to be at least 4 times the size of the maximum aggregate, and the thickness has to be 1.5 times the maximum size of the aggregate, the nominal maximum particle size, the definition that we spoke of earlier. Getting the samples ready, you want to avoid distortion, bending, or cracking during the removal from the pavement. Store them in a safe, cool place. Separating the specimens layer by layer should be done by sawing or some other suitable method. Specimens have to be free from any foreign material such as crack seal, tack coat, subgrade, anything else that would be considered a foreign product. You need a balance, some type of a wire that would go from the bottom of the balance to a basket or something else in the water bath, a water bath, and a flannel or terry cloth towel. Water level needs to be at the overflow. It needs to be at 77 plus or minus 1.8 degrees Fahrenheit. You'd immerse the sample in the water, as shown in this picture here, for 4 plus or minus 1 minute. You'd remove it. You'd blot it with the freshly wrung out. You'd want the towel to be wetted, and then freshly wrung out, and record the SSD mass. You would tare your scale, put the sample into a pan, record that mass. Then you'd put it into a forced draft oven at 230 plus or minus 9 degrees. If it's a 5.5 inch or 140 millimeter sample, you would leave it in there until it breaks down and the particles are no larger than 2 inches. You would dry the specimen for a minimum of 3 hours to determine the mass. You determine the mass at 2 hours interval until there's no change in the mass, and you cannot leave it in for more than 24 hours. You would then cool it to room temperature and determine the dry mass. Method C, or the core dry, it's a apparatus that we put the material in and run it through the core dry. It basically will vacuum out all the water. It will give you the results. It's best on when it's used for in-place cores or cores from a roadway. You have to allow the cores to warm to room temperature, blot them with a towel, put them in the wire mesh basket in the vacuum chamber, and run that following the manufacturer's recommended and the recommended procedure. These are the procedures for running the core dry. Turn it on, allow it to warm up, allow the cores to go to room temperature, place them on its side, make sure that the moisture trap is cleaned out, placing a lid on the chamber so that it will create a vacuum, pressing start. Core dry cycle will run. Once it's done, it will stop, and you can record the dry weight and use the dry mass. Calculation to determine bulk specific gravity is your mass of the dry sample in air divided by the mass of the sample in air minus the mass of the sample in the water. We have to figure out percent relative compaction. It's the bulk specific gravity divided by the maximum specific gravity, or the Rice value. Air voids is the Rice value minus the bulk divided by the Rice times 100. To convert specific gravity to pounds per cubic foot, you use the number 62.4, which is the bulk weight of water, 62.4. Talk about a compaction test section. Oop, apologize, I went too fast. The information on the compaction test section is found in the CDOT procedures. Test section of the road is constructed to determine the number and types of rollers to be used and how effective they are. On CDOT projects, the test strip is done with the first 500 tons of production, with the first 300 tons placed and the contractor using whatever procedures they want to determine their process. The last 200 tons is used for the density test and to see how effective the contractor's procedures were. The contractor determines the methods, and again, does that in the first 300 tons. Then uniformly over the final 200 tons, the procedure is done. All the data should be collected: type and size of rollers, tire pressures, passes, surface temperatures, so on and so forth, from this list shown on this slide. After that final 200 tons is done, there are 7 random nuclear density tests. Then they will do duplicate cores, or 2 cores from the footprint of each nuclear test. The contractor will take one of the cores. The CDOT or the owner will take the other core, and they use those to calibrate or correlate their nuclear gauges to what was done from the cores. You average the density from the 7 cores, take those, add the numbers together, obviously divide by 7 to get an average weight. Acceptability of a test section is in section 401.17 of the CDOT spec book, and it talks about a new compaction test section needs to be constructed when a change in the compaction process is implemented. That is, typically they bring in completely different equipment, and it may be required for different layers of pavement. Each layer should have its own compaction test section. Actual core results, not the correlated gauge results, are what should be recorded into the CDOT program. Click on the CTS button in the program to record the core results and determine the acceptability of the compaction test section. CP82 provides for the development of a correction factor and should be valid until the ingredients in the mixture change or an underlying materials change. This is why it is different layers require a different compaction test section, because they're typically not the same material. May also be used whenever variations in conditions to bring the moisture density gauge into question. If the numbers start being erratic or varying, it may do another correction or correlation factor. This is a form out of CDOT's manual. You can obtain that. It will give you a place to put the 7 test locations and the different factors that need to be. Cores should be handled in a similar manner by everybody. They represent the samples. They can't be bounced, dropped, because it will affect the overall density within the core. So they have to be kept out of the cold or kept out of the heat. Store them on their longest side, never stacking them, wrapping them, transporting them in a tight container, because it does take a lot of time and money to resample. Talk about density and percent compaction of a compacted mixture using the nuclear method, which is CDOT CP81. We're going to do the internal or in-place density of materials using a nuclear gauge. CP15 requires that the nuclear gauges be certified properly. They have to be run across a set of blocks to be verified that they are accurate, that they are reading accurate for all kinds of things. There's stat and drift tests. They have to be calibrated. There's a thin lift gauge. So all of the things have to be done. And all of these CP numbers out here talk about how those things are going to take place. So this is a very simple test. You have a gauge and you have a portable reference standard. You have to standardize the gauge each day on the project. It has to be done on the project or within a short distance of the project because the atmospheric conditions will change and that can affect the gauge. We're going to run the tests and we're going to do the calculations. So to do the standardization, you turn the gauge on and allow it to warm up for a minimum of 20 minutes. You allow it to stabilize according to the manufacturer's recommendations. The Campbell Pacific gauges, you have to take them out of hibernation and because they are always on, and then let them stabilize for 1 minute. You want to check the operation by placing it onto the standard block. Each manufacturer has a different way of putting their gauge onto the standard block, so it's important to understand what type of a gauge it is and how it goes on the block. For the Troxler or Instatek gauges, the handle goes opposite the metal plate. On the CPNs or the Campbell gauges, there are bumps and it will only go on one way. You would take a 4-minute base count and record that. If the reading is not within 1% of the previous 4 standards, you need to rerun the standard. We're running a test. It has to be at least 33 feet from any other radioactive source. It has to be free of any large masses of water or hydrogenous materials, taken in the same environment as the actual measurements are going to be taken. When you're running the test, again, 33 feet from radioactive sources, 6 inches away from any vertical projection. The long axis of the test site shall be parallel to the direction of the paving, and the site should be at least 1 foot away from any of the joints. This is the Instatek Explorer gauge, the Campbell Pacific nuclear gauge, and the Troxler electronics. They all do the same thing, just different manufacturers, different Ford and Chevy and Toyota. So to determine if the density test was successful, or to get a successful test, you'd want to make sure the surface is free from any loose materials and deformations. The maximum allowable void space under the gauge shall not exceed 1/8 of an inch. Optimum condition is when the gauge is in total contact with the surface. One way to do that is to use a mineral filler or sand to fill the voids. The depth of the mineral filler, again, should not be greater than that 1/8 inch, and the total area filled should not exceed 10% of the bottom area of the gauge. Test location should be 1 foot or more from a confined product or an unconfined longitudinal joint. Set the gauge to the MA or the backscatter mode for testing asphalt. PR is for soils, which you're then going to read dry density versus wet density. To verify that the maximum mixture density that represents a mix, you have that. The rice value. Average daily rice value is then converted, input into the gauge if available. If not, you're going to do it by hand calculation. You'd verify any correction factor for the gauge is being used and accurate. Run the test by lowering the probe into the backscatter position. Select the wet density reading on the gauge. Ensure that the rod is securely locked into the bottom notch or the backscatter position. Set the gauge flush on the asphalt pavement. Perform 2 1-minute readings. Record each of those readings. Rotate the gauge 180, or mark where the gauge is sitting, then rotate it 180 degrees, taking 2 more 1-minute readings, recording all the data from each of those readings. Test results can be affected by a lot of things. Chemicals, water, other things can affect the gauge. So it's important that when these tests are being taken, they're being taken accurately to represent what is being placed on the surface. Using wet density, you average your 4 tests, divide by 4 to come up with your average, taking the 4 tests, add them together, divide by 4. Apply or add the known correction factor. maybe add, maybe subtract, but apply the corrected factor. Divide the adjusted wet density by the lab maximum density to determine the percent relative density. You can convert the specific gravity to pounds per cubic foot, again using 62.4. At our altitude and elevation, we use 62.4 for the weight of water. Average the 4 1-minute readings. Calculate by adding the field density obtained from your compaction test section. Calculate percent density by dividing the field density by the laboratory max. With that, we have come to the end of level A. You should now be able to review this over and over to feel comfortable with what you're doing. Level A certification will be done in 2 parts, written test and laboratory proficiencies. Thank you for watching.